So I'd like to kindly invite him to deliver his keynote speakers. Thank you so much. Harald. Appreciate it.
Thank you very much for this very kind words. I'm very honored, and I'm also honored to be part of the Black Sea conferences, and it's a great initiative. Wireless communications, telecommunications is a global challenge, and we need to make sure that everyone participates in that journey. So let me also like to thank the organizing committee for inviting me here, and let me talk about LiFi or live fidelity, which is a technology that uses a particular range of frequencies for data communication. But before I do that, you may not be familiar with this concept of light communication. So that's why I've got a little animation here to illustrate the main principle that we use. First of all, we use some digital content that we have on a tablet or a computer, and we have a connection to an LED light source that has a gray box, and that gray box has some electronics in order to convert AC signals to DC signals. So what we do is we add additional electronics, a microchip, in order then to encode a binary bit stream into intensity variations of the light source. In that case, it's on-off keying, simple way to transmit A1. When we turn it on, we want to transmit A1, and we turn it off when we want to transmit a binary 0. Very simple. And we can do that with lighting because LEDs are electronic devices, and unlike incandescent light bulbs, the frequency, the intensity can be switched very quickly. And then we have another gray box here at the receiver, which is a photo detector, and then use sound connections to inside a computer or a smartphone then to then display the content. So that's the principle of what's originally called and introduced by my colleague Professor Nakagawa at Keio University as visible light communication. So we take this as a principal way of transmitting data, but LiFi is not only a point-to-point communication link. So visible light communication transmits from a static transmitter to a static receiver, whereas LiFi is a complete mobile communications networking layer, which I'm trying to introduce today. So the reason why we've been looking into this part of the electromagnetic spectrum, i.e. visible light, is illustrated with this figure I've shown here. This is the radio frequency spectrum map of the United States from 3 kilohertz to 300 gigahertz. So it covers the entire radio spectrum. And you know that wireless communication systems are operated typically GSM in the 1 gigahertz region. Then we have Wi-Fi 2.4, 5 gigahertz. Now we are entering basically this region of the frequency band, and you notice that is we're coming almost to the end. So the 300 gigahertz is the end of the radio spectrum. And at the moment in 5G, the main technology that's been used is, or considered, is millimeter wave communication, and that is between 30 gigahertz and 300 gigahertz. So the very last sort of part of the resources we have, and we believe usually there's lots of spectrum there, but if you look at the spectrum map, actually it's quite heavily used by radio astronomy, by other military applications, defense applications. So, first of all, the spectrum is fairly heavily occupied. That is one message. And if we are led to believe of what Cisco white papers tell us, with an exponential increase of data rates, we are running into what is called the radio frequency spectrum crunch. That we don't have enough resources to transmit data. And I think it's very important to recognize that at the moment we are experiencing the third industrial revolution, which is all around data and data communication. And if you look around, if you look at all the big companies, all big companies deal with data. Whereas the second industrial revolution was all about industries that are very energy intensive. Now, our third industrial revolution is all about data and data resources. I call this the oil well of the third industrial revolution is running out. And that's why we've been looking into different ways of supplying data to all the economies and also people that use mobile phones and computers quite heavily. But before I do that, let me give you one comment about millimeter wave communication. And I think it's a big hype around that technology, but we cannot beat physics. The law of physics exists, and what I've shown here is a very simple equation that you may or may not know, free space equation. We know that the path loss L is proportional to the square of the frequency. So if we do a simple analysis, if we move from 3 gigahertz, which is the current 4G spectrum, to 60 gigahertz, we incur an additional path loss of 26 dB. And that is added to the link margin. So we need to recover the 26 dB in loss. We don't want to increase the transmission power by a factor 400. We don't want to do that because we want to be energy efficient. The only way that we can recover that is by applying beamforming. And that imposes a number of challenges, because imagine you have a receiver in your mobile phone, you have an antenna array in your mobile phone, you need to form your beam to where the transmitter is, the receiver is, the base station, and then you need adaptive beam steering. You need phase shifters at the receiver, at the RF front end, and that is very expensive components, and then energy inefficient components. So there's a number of challenges that simply come from this law of physics that we have to recognize. And then also, basically, this law also applies to the visible light spectrum, but there's a unique advantage with the visible light spectrum, which I've shown here. First of all, if you take 30 gigahertz of radio spectrum and multiply by 10,000, we end up in the entire spectrum that we have available in the visible light domain. It's 300 terahertz of spectrum. It's not regulated, it's free for us to use. So there's no government who is demanding funds for it. And it's safe, created life on the planet, and it's already installed. If you look at the ceiling, you have light. In this case, it's fluorescent light, but you see more and more LED lights. So you have it actually installed. You have visible light transmitters all around you. So there's no need to add new infrastructure. It's there. So these are the few advantages that we see. And there's another trend that is very important to recognize, is that when we move from second generation wireless communication from GSM, which is mobile telephony, to mobile multimedia, from the second to the fourth generation, there was only one major concept that led to improvement in cellular communications, which is not MIMO. It's not some fancy technologies, it is the small cell concept. And that is another way to combat the increased path loss by simply reducing the cell size. Because then you basically have a shorter distance, and the distance affects the path loss as well. So if we look at, this is by the way, a beautiful city of Edinburgh here. It's also at the sea. It's a very cold sea, it's the North Sea, but it's a city of about 400,000 people. And if we go to the second generation GSM, the maximum cell radius was 35 kilometers. So a radio cell was 35 kilometers in radius. Basically, you would need it for that city, probably one base station somewhere in the center to cover the entire city. In the third generation, the data rates increased, it went to multimedia. So you talked about 2.5 kilometers in cell radius. If we go to the fourth generation now, the intersite distance is 250 meters roughly. And again, you see the infrastructure effort, and what comes with that is another challenge is the backhaul, because all these base stations need to be connected in some way, and that poses another challenge. And I guess I don't need to tell you what will happen in the fifth generation. I can't even plot it, so the intersite distance, cell radius goes down to about 25 meters because of the beam forming and the additional pathways. Now imagine about the infrastructure that you would need to generate. And also if you imagine a room like this, you can't simply add 4 radio access points at each corner of the room because you get another effect, which is interference. And especially if you look at Wi-Fi, as a potential-based transmission multiple access technique will reduce the sort of data rate in that environment. So our vision of LiFi is moving away from the point-to-point static communication between an MVP and a receiver, is to consider this installation in that environment as a cellular network. You view that, we view this generally as a lighting network. I view this as a wireless communications network which is already installed. What we need is little devices. We have a chip there on the left side corner, which is a 2.8 by 2.8 millimeter size die on CMOS that houses 49 detectors. So what you have there in 2.8 by 2.8 millimeter is a massive MIMO receiver. And that we need to get that receiver into the smartphone, and you may have seen rumors that Apple is now having LiFi capability in their iOS 9.1, so that industry is already thinking about light communication. And we see this as an additional layer of small cells within the mix of existing so-called heterogeneous wireless networks. To show you in a picture what we think, what we mean by that, is that we keep radio. Obviously, we have the radio base stations outside. We have the picocells, we have the femtocells or Wi-Fi, but then we have, in addition to Wi-Fi, we have every single light source here is an individual access point covering a 10 square meter big cell. And that we have, already in that room, we have 1, 2, 3, 4, we have 12 wireless LiFi access points serving 12 times the capacity of a single access point, and that's not possible with radio because of the interference I've mentioned, and that is the vision of LiFi. So there's a comment, so we've done some work that you see in that paper that I've shown there, is obviously we need good channels and good channel conditions because that frees Harald Haas mode also applies to light. It is important to find out in a room installation like this, what is the probability of line of sight? And we've done certain scenarios, and we started with a cellular hexagonal structure. We have extended it to a Poisson point process, a random DPP process. But let's start with the hexagonal structure. And the left-hand side, you see the white color means high probability of line of sight, which is close to the lights. You see high probability line of sight. And the room walls, you see a reduction of line of sight because you slightly come out of the cone of the LED light source. And it's important now, if we look at this graph here, that tells us what's the probability that the line of sight is above a certain probability. So it's important to recognize that in 90%, with 90% certainty, the probability is greater than 90%, which is a strong message of creating a very high chance of getting a line of sight with a light link in our scenario like this one. And that's very important to recognize. I've shown you the concept, and I would like to also show you that a concept is already real. What you see here is a LiFi access point that you see there with a little black square. That's an infrared filter for an infrared uplink. So we need bidirectional communication. And that dongle here is a USB-powered dongle you put into your laptop, tablet, computer, and you have a LiFi connection. And you see two elements here. You see that one here is the receiver, and then it's the infrared LED for the uplink transmission. And that has been demonstrated at Mobile World Congress this year in Barcelona. With that system, you could allow multi-user access. So you had one dongle sitting under one light. It could be served by one single access point, and also this system would allow handover. If you would start your Skype call in that corner, and let's assume all the lights would be LiFi enabled, you could roam and walk, and you would be handed over from one light source to another one. That is realized and implemented here, and it's, I believe, the world's first fully LiFi system. The access point is now being integrated into an LED luminaire, so that you will get at the end of this year a complete product, which is a LiFi luminaire that you can buy off the shelf. This is where we are with that technology. So it's not beyond the concept stage. The advantages are obviously higher security, and physical layer security in a cyber crime world is very important. Many headquarters, company headquarters don't have Wi-Fi because Wi-Fi leaks outside. If you had a room like this, light wouldn't go to walls, so you create a more physical layer secure environment. It's more energy efficient. It allows localization for indoor navigation services. The data density can be increased by 3 orders of magnitude. So that the goal in 3GPP is to get to 100 megabit per square meter. We have not reached that yet, so it's still below 1 megabit per square meter. With LiFi, we have shown we can go up to 1 gigabit per square meter in data density because of the fact that light is very contained and it has greater safety. So let me explain to you the security feature, but I think it's self-explanatory. If you open up your Wi-Fi network in your smartphone, you probably get 20, 30 Wi-Fi networks, which means you have access to them and you could break into them fairly straightforwardly. And that provides us the security vulnerability. In LiFi, if we had LiFi in one room and you have opaque walls like the one here, you would be ensured that no light would leak into the other room. So if you would then open up your LiFi networks in a room that doesn't have a LiFi light, you would not get any signals, and vice versa. And that provides a huge security benefit for various applications. The other one is localization, and localization can be combined with security. So imagine this is your office environment where you have the CEO office, you have secure file servers, you have conference rooms. With LiFi, you can partition a network, a wireless network, and the access to it in a fairly rigid and unique way. You could, for example, give different access rights in the CEO office to the network, and you could give different access rights to the network in the office space. And what we call here is we are geo-fencing as well. You could have one access point that you are served, and then you may only have the neighboring access points that you can hand over to. So that would ensure if you create a system like this, and if you then walk, the fence would walk with you. So no one, imagine this is a Starbucks coffee and somebody fakes a Wi-Fi access point to that corner, you could basically be hacked or basically be fooled at the other corner. This wouldn't work with that system because somebody here would not have any access to the other side of the room, and so would not be tampering with your access. So that's providing a very good way of enhancing security in a network. Let me also give you a few words about energy efficiency. So what we've done is we've taken a 5,000 square meter office environment. We have a room size of 100 square meter, 10 by 10 meter, basically large office room. We vary the number of users. We have 50 rooms. The light coverage is 10 square meter, which is a realistic assumption. And the lighting power is 15 watt. And that's for illumination only. Then we have a Wi-Fi access point covering 200 square meter, so basically 2 rooms, which is, I guess, reasonable. And the power of Wi-Fi access point is 12 watt, which is also a fairly realistic number. And then the LiFi access parameter is that we assume only 50 megabits for a LiFi access point. And that is because we use these phosphorus-coated LED light sources, and it covers 10 square meter, and the additional power we need for data communication is 5 watt. So the LiFi light fixture totally requires 20 watt. And now we brought the energy efficiency in kilobits per joule here, and with the increase of number of users. So first of all, for low number of users, Wi-Fi has a much better energy efficiency because of the 1 gigabit per second data rate that we can get through. And with a few number of users, there's less contention, there's less run and backup, there's less retransmissions, and therefore there's very high energy efficiency with Wi-Fi. But it drops off very quickly because we come into the contention mode, we come into random backup, we come into retransmission states which require energy. And that with that we lose energy efficiency, whereas with Wi-Fi, because it only covers 10 square meter, the contention state happens far later. So we started off with lower energy efficiency because of only 50 megabits, but then keep it fairly stable over a large range of users that we serve. And if you plot the ratio of energy efficiency between LiFi and Wi-Fi, we end up at, say, 100 users of a gain of about 100. So we have a 100 times improvement in energy efficiency with LiFi. So there's a number of misconceptions that LiFi cannot be dimmed. That's not true. We can dim it and also transmit data. The lights won't flicker because the lowest frequency we operate is 1 megahertz, and your computer screen is 100 hertz. You don't see a flicker on the computer screen, so why would you use the light? It's not only for downlink, it's for uplink. The sunlight will have no effect. It's because we don't use on-off key. We use a form of OFDM, which is a purely AC coupled modulation technique. And sunlight is a constant light source which we filter out as long as we don't saturate the receiver, which can be maintained by easily with automatic gain control. The lights have to be on in a certain extent, but the power for communication is only 5 watt compared to 12 watt or 15 watt for the lights. And it's a line of sight technology, which is not true. And that's one of the greatest misconceptions. It also works off reflections. And let me show you a little video that we have here. We have a LiFi enabled off-the-shelf LED light, downlighter there. We have an access point connected to the light. We have the red circle is the infrared filter for the uplink. The thing in the front is about 3 meters. Is the receiver dongle connected to the USB, and we transmit a video. Now we turn the light around. The video stops slightly. This is adaptive modulation coding kicking in. But now the video resumes with a lower order modulation scheme in place. But still transmitting data, although there's no direct sort of pointing into the receiver in that case. So it's basically working now off with a non-line of sight scenario, only from the reflection. So it's working like any other communication system. There are components is another misconception, and there are, for example, lots of LED components. So what we plot here is a different technology roadmap of LEDs. What we have now, when you can buy, is these blue LEDs that have a phosphorus coating to make it white. And that phosphorus coating slows down the frequency response. That's why you get with current LEDs about 100 megabits per LED. That's sort of the upper limit. If you go to RGB, we talk about 5 gigabit per second demonstrated. With gallium nitride, very small LEDs that have a very high frequency response. We have done recent hero experiment with a wavelength distribution multiplexing getting 10 gigabit per second, and we have also shown with laser LEDs we can go up to 100 gigabit per second. So that is really exploiting the full capability of the available spectrum. In terms of modulation, we can show with a single gallium nitride micro LED that's shown here that we can transmit up to 3.5 gigabit per second with adaptive bit and power loading that you see on the left-hand side. We have the frequency response of the micro LED. The 3 dB bandwidth is about 60 megahertz. But unlike radio, you don't have to comply with spectrum masks. If the channel bandwidth is, the cutoff frequency is 30 or 60 megahertz, you don't have to stop transmitting there. Basically, we use the very smooth and softly decaying transfer function to modulate the LED far beyond the 3 dB bandwidth, and then apply bit and power loading. You see the bit loading and down the power loading. And with that, we can load the channel and get almost complete channel capacity out of such a system. In that case, with a single LED at 3.5 gigabit per second. I told you about the components. This is the receiver chip I've shown you earlier. You see the 49 7x7 APDs on CMOS. It's a massive MIMO detector. And that is a LiFi chip that tries LEDs direct at 4 chains. So we can use it as a MIMO device or a what we call ganging device, transmitting 1 ampere at 500 megahertz. So with that chip, we've driven 1 gigabit per second to basically just connected an LED to that. And here's our RGB system. And what we can also do is sort of what we do in radio is use something like a Talbot effect to create angular sensitivity. So beamforming can be done at a receiver as well without any hardware, without any electronics, without any energy. What we've done is a metal grid. It's a metal layer on top of the sort of the CMOS structure, and that we created like a blind system where you have sort of a different structures of metals and metal, and then what you see here, you get light through, and the Talbot effect says that you repeat the incoming pattern regularly. And then what you see here is if the angle of the light sort of changes, you have certain angles which are beneficial, you get light through that blind system, and in other angles you block the light, and so you get angular sensitivity for interference mitigation in case of multiple access points. All of that is possible, it costs 0 energy. It's a simple sort of manufacturing structure process that we've implemented on this chip here. And what we can also do is, the micro LEDs have a size of 550 micrometer. This is the transmitter chip I've shown you opened up. It's 4 by 6 millimeter, and we have wire bonded 16 micro LEDs on top of the chip. So we have the most compact LiFi transmitter system here that you see. We turn on these micro LEDs one after each other, and I'll show you in a minute that with a single LED we can transmit 1 gigabit at 10 meter. So we have 16 here, and this is a massive MIMO transmitter at a size of 4 by 6 millimeter. The receiver chip is 49 detectors, 2.8 by 2.8 millimeter. Really great, you can take the MIMO concept to new levels. You see them all active now. So furthermore, we've been looking at solar cells as data detectors that you see here to come to another very important aspect in when we go to Internet of Things, is that you may have 100 devices around your space, and you don't have to charge them all the time or replace batteries. So devices need to be self-powered, and energy harvesting is becoming a great topic in radio communications. But with light, we have devices that can harvest energy very efficiently, solar cells. And what we have looked into here is, can the solar cell also act as a detector? And with that 30 by 30 centimeter solar cell, we've been managed to achieve, again with OFDM and bit power loading, we've achieved 15 megabit. With new LEDs, that's demonstrated at TED Global last year. And so the idea is that if you have your remote hut somewhere, you have a laser pointer, a laser station at a hilltop, and basically you distribute the internet to remote areas, to the roof of villages and houses. We can do this with free space optical communication, but the receiver is basically of this size. And if you imagine 5 kilometer distance, to hit the target in a very small receiver is very hard, and you get outage. Strong winds basically shake the pole. But the solar panel's roof is very huge, and it doesn't really matter where you hit the solar cell. You have a very robust, reliable connection for the rural light. And also for the mobile phones, they could have embedded solar cells that harvest energy from the ambient light, which is not interference, it's useful energy we can harvest, and then the solar panel acts as a receiver for light. So here's an example where we've shown that with a single micro LED, we've transmitted 1.1 gigabit over 10 meter with that system. I have a little video here. So here's the little lens, it's a little beamformer, costs less than $1. And this is the micro LED. It's the micro LED array. In fact, it's 20 micro LEDs, but we use only one here. And that is connected to a National Instruments PXI, which is a full physical layer OFDM implementation. So this is the receiver. It's an APD with a 7 centimeter sized lens, polymeric again, a beamformer. And you see the LED there. This is the transmitter, and this is the high definition view we get. So we stop the link, block the link, obviously video will stop. And if we unload the link, the video from that light source, from that single, you would assume that is an uncompressed video, uncompressed, uncoded, plain communication. You see the bit error performance you see with the naked eye is very good. And also at 1.1 gigabit with a single transmitter. It's 4.5 milliwatt optical output power. Now we've looked into a laser system. Now let's assume we have 3 different RGB lasers, create a white light beam, and then misuse the laser in diffusing the light rather than collimating the light. We diffuse the laser beam. We get 1 square meter white spot, which is in our view the next generation of lighting. And with that, and assuming 9 colors at 15 nanometer spacing, we can go up to 100 gigabit per second, and that's also demonstrated in that application that you see there. And lastly, let me also give you a comment on the hybrid nature of Wi-Fi and LiFi. What we've shown here is a room with LiFi access points and Wi-Fi. The red dots are users covered by Wi-Fi, and we have a scenario where we have overlapping spots. We've then developed a simple load balancing algorithm that is based on the signal to interference plus noise ratio, SINR. And whenever the SINR of Wi-Fi is higher than the SINR of LiFi, the user will be served by Wi-Fi. That's why you see in the interference regions, you see red dots. That means that users are covered by Wi-Fi. The important message here is that with that system, we can help Wi-Fi to get more effective throughput because we take away users from the Wi-Fi system, hence reduce contention and then retransmission and overhead, and Wi-Fi gets a much more sort of fluent way of serving users without loss in spectrum efficiency, and LiFi will get sort of also some load. And that is a message that LiFi should not be seen as a competitor to Wi-Fi, is a system that would help make Wi-Fi systems even more efficient. Applications are ranging very, very, very far. That's one of the great advantages. So we can use street lamps to create our 5G cellular network within the sight distance of 25 meters. We can use cars and street furniture to transmit information for intelligent transport systems. It would work underwater. Divers could have more secure underwater missions because they couldn't use light to exchange data. The Internet of Things. We have LED lights in all our electronic devices, appliances at home already. Imagine 5 milliwatt optical output power. I've shown you, this could transmit, the fridge could transmit 1 gigabit to the lines. We can have e-health. We have wearables, in that case, a smart earring can transmit body data, blood pressure, temperature, sugar levels, and then basically monitor an aging society regularly. Indoor navigation, advertising, intense environments like Stadia, Wi-Fi will not give you individualized replays of players. You can use, however, the lights to create this high three orders of magnitude improved data density. Intrinsically safe environments where radio doesn't work, oil platforms, petrochemical plants, hospital environments have lots of devices which are Bluetooth connected, and also cars. And I heard recently that the greatest security weakness of modern cars is not the lock, it is the Bluetooth-enabled valve of the tire, where people break into the car system and basically crack the car. So Bluetooth A in a hospital environment where you are connected to a sort of a life-threatening, life-saving machine, you don't want to have anyone tampered with that machine, and therefore the security that LiFi provides is a very good way of doing it. The rural divide, and what LiFi does is it combines the security that we know from fiber connections or wire connection with the convenience and mobility. So let me give you, if I may, a few on the commercial side and the commercial view of LiFi technology in the future. At the moment, what we see the lighting industry basically in a disarray. You may have followed that Philips lighting was floated on the stock market last Friday or Friday before. So Philips sold Philips lighting business. This is because LED light bulbs last 20 and 30 years. So the business model of selling light fixtures has gone. And the lighting industry is now looking into light as a service. So lights in the future will do much more than just provide illumination. So the lighting industry basically takes market shares from the wireless industry. And this is a pull mechanism with light as a service. If that is the case, and with the wireless communications and spectrum crunch, the wireless industry has a unique chance to extend into the lighting field via the push 5G and IoT. And the interesting thing is, the metric in the lighting industry will not be dollar per light bulb, it will be dollar per bit, because light as a service is the domain that it's entering. The same metric is in the wireless communications, dollar per bit. So there's the same metric, a market metric, that governs both industries. That's why you see both of them merging. It's like a bit like the camera sensor that when you went from analog photography to digital photography. There's been a landslide shift in the industry, and some industry basically were wiped out, and others flourished because they realized the change. And that is the change that we see. So light as a service means that this incandescent light bulb will become this, with an operating system, with a full computer inside, where the light does one thing, illumination, but 100 more things like smart sensing and so on. Like we had 25 years ago or 30 years ago with a mobile phone, which was mobile telephony, which is sort of analog to the light bulb, and now this is a smart computer. And this is the same transition that we see will happen with the light bulb. So this one and this one, this is what we see 28 years from now. A computer with thousands of apps running on that light source. So the conclusion is, therefore, if you go into the generations of wireless communications, third generation to second generation, we had a paradigm shift from analog to digital, which was massive. The mobile telephony was a service, and that, in my view, and others as well, was a revolution. 2G to 3G, 4G to 3G to 4G, 4G to 5G didn't have a real paradigm shift, and the idea was evolution. And there's an evolutionary step through these generations, with a small cell concept being the real paradigm shift in that transition. And the mobile internet was the pulling service, and that is a revolution. So my hypothesis is that if we move from 5G to 6G, we will move from RF to light. And the Internet of Things will be the application driver, and this will be a revolution. And I'd like to show you that. Hope you can join us in that revolution. Thank you.
A few minutes to have some questions for Professor Harald Haas. Yes, there are several. Let me just start beginning right here. Okay.
Thank you very much for an interesting talk. One of the hats I wear in the Comstock Communication Society is to chair a board that oversees the standardization projects that Comstock sponsors, and Alex actually is partners in that crime with me. So the question is, any standardization work going on in this area?
Yes, indeed, thank you for the question. There's 802.15 subgroup 7 that is currently standardizing LiFi, and there's two strands of that standard. One is the camera communication, low rate, simplex communication. The other one is LiFi, which is basically the company I spun out, LiFi, is an active player in that standardization. But what we recognize now is that this standard may not be the ideal fit. LiFi may be better fitted to Wi-Fi 802.11 level. And that is something that we've been seeking advice and also partners to move that standardization into that group, because it's a mobile communication system rather than a metropolitan backhaul kind of system.
So why join the enemy in a way, and Wi-Fi, which is 802.11? So why don't you come to the Communication Society? We carry out this standardization African Communication Society instead of Computer Society. We can talk offline.
We can talk offline. I'm very open, as I'm not absolutely familiar with all the standardization activities of Console, but advice is highly appreciated.
I'm not those are our friends in
for the nice presentation. As a Wi-Fi guy, I'm convinced to use LiFi under some circumstances. But I'm also wondering about the challenges and limitations of implementation.
Okay.
So, everything seems very nice, but can you also tell us the other side? What are the challenges of implementation? For example, bringing data to all these light lamps, like access points, or other limitations in the implementation.
So you touched upon a very important aspect, which is getting data to the light. But the good thing is that all the lights that we have here are already connected to some network. It's a power line network, and there's a technology called power line communication, and that's a very nice home for an application for power line communication, also standardized to make a good use for that technology. The other is, if you look into a modern lighting installation, you don't find a power connection to modern lights. They have an Ethernet connection and use power over Ethernet. With power over Ethernet, you can supply 60 watts to the device. And that's been done, for example, in the Deloitte building in Amsterdam, the Edge building, where they have completely revamped the installation into power over Ethernet enabled lights. That's Philips Lighting that did that. And they saved 30% of installation costs and did the installation 50% of the time. So modern installations will use power over Ethernet lights, so we have the backhaul in that way installed. So that is, I don't really see really a challenge. The challenge is in the minds. I'm convinced, been working on that for 13 years, there is no technology challenge. And the implementation challenges like the beamforming and things like that, they cost $1 here because it's a lens, whereas in radio they cost tens of dollars because you need multiple power, RF chains, you need sort of electronics, you need energy and power to do that all. So it's a mindset issue in opening up our minds in the radio communication community to realize that radio is only one part of the electromagnetic spectrum. And I would like to get this message across that we should be out of the box thinker and not be limited to a standard way of thinking. And there may be other ways of looking into terahertz communication where there are no devices, would be the challenge there, or into UV communication. So we've shown that with also the product here with the LiFi. We know it can work as smoothly and as reliably and even more reliably than Wi-Fi. It's just getting people accepting that radical shift.
There was one question here. First of all, I would like to thank you for a very interesting talk, and then a couple of questions, maybe just for some clarification. First of all, I wanted how to mitigate interference between different cells. You mentioned you want to use angle of arrival. Yeah.
Yes.
And sure, maybe you also will be using some orthogonal techniques, some orthogonal codes, orthogonal signals, and so on and so forth.
Yeah, I think you touch upon an area which we have looked in quite intensively over the years. We can obviously use standard mitigation techniques like frequency reuse, soft frequency reuse. That's all done and all shown that we can also frequency reuse in that case. But angular diversity seems to be a very powerful mechanism because if you look at a detector, it has 49 detectors, and if you create a semisphere of micro lenses around it, you can imitate an insect eye. You know a facet eye of an insect, where certain detectors look into certain areas of the sphere, and then if you have one detector, and you can apply sort of combining algorithms, and if you get one strong interference signal, you can attenuate that signal, you can basically blind that detector, and only activate those detectors that look into the desired direction. And the directionality of light is a very unique way we can explore that feature. So that's
but also you mentioned is that this technique can be used for non-line of sight communication.
yes.
And will it be possible to use such techniques with non-line of sight communication?
This
There is mitigation
okay.
and loss communication.
Yes, but bear in mind, 90% of the cases we have line of sight. So it's very powerful. In cases where you don't have line of sight, you would then resort to casting interference, cancellation techniques, mitigation techniques, or frequency reuse. So it's this hybrid mix of a toolbox of technologies we can apply.
And my last question is connected with link transmission. You mentioned that you like to use infrared communication. And I'm not a LiFi guy, so I don't know what is expected rate for uplink infrared communication. My gut feeling maybe it is a little bit or much smaller than downlink communication.
Yes, I think
about it. And you know, in modern networks, uplinks becoming very, very huge because of cloud services, because of huge upload to the cloud and so on and so forth.
Yes.
So how would you like to cope with it with LiFi technology?
I thank you for this question. I've shown you the dongle where we have an infrared LED, and I can tell you that the capacity is symmetric.
Okay.
So we get 40 megabit uplink and downlink. It's because the detectors that you get off the shelf are more optimized for infrared spectrum for natural reason than for visible light. So you get also better reflectivity from sort of objects in the infrared spectrum as part of the channel models that need to be developed. So this is actually that doesn't provide a limitation. It's a way that we need to make sure that we remain within the eye safety regime of the transmitter, but it's only a single transmitter as opposed to serving multiple users. So therefore you can reduce the transmission power with modulation technique that will not provide a constant output like in lighting. We would then have optimized modulation techniques for the infrared. And that's very important that the techniques, both directions will be different.
Thank you.
Thank you.
We don't have enough time anymore. Actually, if you have more questions, I think in coffee break we can ask some questions.
Okay.
Professor Harald. But let me just add one thing. This is one of the new emerging technology. We've been also collaborating with Professor Harald, and I am encouraging especially young researchers here to get into this field, and then I'm sure you have lots of interesting research results. I am very much pleased actually to present this plaque to Professor Harald about this excellent presentation and make this very excellent topics.
Optical communication. Thank you.
Okay, thank you so much.
Thank you very much. Thank you very much. Thank you for the
we have to give out one more plaque because the Technical University of Sofia rector, Professor Georgi Michov, will not be at our banquet, so we have to deliver him the plaque, and we'll ask Professor Vladimir Popov to receive it on his behalf. And we're really very grateful to the Technical University of Sofia